Let's start to record. Okay. So this is the second part of our lecture on how to predict the value of a policy and how to control using function approximation. Okay. So in the second part, we will focus on control. So what we did yesterday was to set up a framework to perform systematically the learning of the value of a function without having a model. So we always remember in the model-free setting by using an approach which is inspired by gradient descent, but then sort of parts away from gradient descents by using bootstrapping, that is, by approximating the target of your loss function, if you wish, which is the value error, with an estimate which is constructed by the current estimate itself. Okay. And even when we use these semi-gradient methods, we've just been writing this down as a pseudocode, and then I gave you the theoretical result that these algorithms converge, and basically the problem of how well they perform in approximating the true value of the policy, is a matter of how good basically your approximation is. And in particular, in the case of linear approximations, in which you can express your value function as a linear superposition of vectors, basis vectors, which are called also features. In this case, you have theoretical guarantees about how far you actually are from the best that you can get. Okay, so this is the linear situation is essentially everything is kept in check in the theory. In the nonlinear case, for instance, when you use artificial neural networks in order to approximate the value of your policy, in this case, there are less theoretical guarantees, essentially because the problem is nonlinear, and therefore you might have more than one point to which the algorithm can converge. So what we want to do today is to see how we can combine these ideas from semi-gradient methods and learning with approximation, with the idea that we also want to have reach optimal control. So we want to approach as much as possible a solution of the Bellman's equation. So it turns out that for a class of problems which are called the situation where you have on-policy algorithms, the situation is theoretically under control. Okay, what are on-policy algorithms? On-policy algorithms are algorithms in which you use the policy to choose actions and also to construct your temporal difference error. So in general, these two objects are distinct. So there is a behavioral policy. Okay, behavioral policy is the policy by which you produce actions. Okay, so this is what really the agent does in practice. And then there is a target policy which produces estimates for the temporal difference error. In on-policy algorithms, these two things are the same. For instance, SARSA. SARSA is an on-policy tabular temporal difference algorithm. Okay, so on-policy because of this equivalence between the behavioral policy and the target policy. Temporal difference because it uses temporal differences to construct the error and therefore the algorithm. it's online, but all the algorithms that we have been discussed are online. But let me add this just for out of online, which means that we don't collect data before and then we use data, but we interact continuously online with the environment. And what else? Yeah, that's it. Very good. So the first question that we want to address is, can we extend SARSA with function approximation? So the idea is basically that we now want to write our Q function, the state action value, which is a function of states and actions in some parameterized form. Okay, so this is exactly what we did for our value function. And now we want to merge this approximation with the tabular. Sorry, yes, tabular was the keyword that I was missing here. Remember, tabular means that you have discrete states, discrete actions, so the Q matrix is actually a table. Okay. In function approximation, this is not anymore the case because it's a matrix valued function of the parameters. In this situation, again, we have two possibilities. For instance, it could be the linear approximation, in which you're writing your Q as a sum over features with some weights W, and then you have some functions which we can call xi, which now are features of both states and actions. Okay, for instance, in robotics, you may have continuous states and continuous actions. And these functions xi are something which is an observable, if you wish, of this continuous state space. Or in the nonlinear case, some artificial neural network, typically feed forward. Okay. So then we basically what we're going to do now is, without much of a ado, just write down the pseudocode which combines these two ingredients. Okay, and we will have a look at it, and you'll see how it works. So this is basically what we would call a semi-gradient SARSA. So the pseudocode starts as usual, providing some input, and the input is some function. Okay, so this must be differentiable because we want to take derivatives of this function, just like we did for the value function yesterday. A differentiable function approximation of the true Q. Differentiable, I mean, of course, derivative with respect to the parameters. Okay, the states and actions here can, in principle, still be discrete. So then you have the parameters of the algorithms, the learning rate, the exploration rate. Okay, and these are positive objects which you fix at the beginning. They might be scheduled. Okay, they might change in time as you perform the and then you initialize the weights for your algorithm W to some initial value. And then you enter a loop, which is the external loop over episodes. Okay. Episodes are chunks of training in which you start, you interact with the environment, and then at some point you stop, either because you fall into a terminal state or because there is some discounting, and therefore you might cut your system short with a certain probability 1 minus gamma at each time step. Okay, so this is how learning episodes are organized. And then at each episode, you initialize S. Okay, so for instance, you take a state S from over a distribution. This is your state S. And then you choose A from a policy pi derived from Q. Okay, so this is exactly the same thing that you do with tabula rasa. So you have some weights W here. From this, you construct your matrix for those weights. And then you pick, for instance, using epsilon greedy, you pick the max of this matrix for your specific parameters W. Once you have that for every state, you for that particular state you chose, capital S, you get action capital A, which is the maximum with probability 1 minus epsilon, or any actions with probability epsilon. Okay. So you have generated an action, and then you loop over time. Okay, so this was the start, the first step to start your episode, and then you repeat. So you take action A, the one that you just generated, and then you observe, as usual, a reward and the new state generated by your environment or by the code, which you cannot know what kind of model it's using. Then at this step, you again choose a new action A prime from pi, derived from Q in the same way, okay? So you repeat exactly the same step as before, and you produce a new action A prime. This is what you usually do in SARSA, okay? The last A is because you have to pick a new action. Notice that we have not changed the parameters yet. So you're doing this twice with the same parameters so far. Then at this step, once you have this, now you're ready to compute the temporal difference error, which in this case is just the reward that you have just observed here, plus gamma. And then you have your Q approximation in the new state as prime and the new action A prime for the current parameter W minus Q at the former action, former state, former parameter. Okay. So far so good. It's just comparing as usual, the reward with your expectation about what the reward would be. So the temporal difference error is always this interpretation of mismatch between what you observe, capital R, and what you had predicted on the basis of your current parameter W through the Q function. Then now you're ready to update the parameter. So you replace your W with the previous value plus learning step, temporal difference error. And then here you put the gradient of your approximation at the state and action that you were in earlier. So notice that the usual structure in all learning algorithms, you can identify here, this is the temporal difference error, this object here, and this quantity here is, broadly speaking, an eligibility. So all temporal difference error mix up these two things, combine them as a product, Okay. Here, the eligibility is the gradient of your approximation. And this is a semi-gradient method because the third delta on the right is not related to the gradient of the error, but it's an approximation thereof. Okay, then you're basically done. You just have to put back the new states and actions into the current states and action, and then your loop closes. Okay, until the episode finishes. So when the episode is over, your next queue here will be set to 0. Okay, if there's no future, you set it to 0. Okay, because at the last step you sort of, it looks like you have to go beyond what the horizon is, what the current situation is. So therefore you set this to 0. But apart from this technical detail definition, you can then repeat this over episodes by, of course, by keeping the same parameters across episodes. So you finish one episode, then you restart with the parameter that you had at the previous episodes, and over again. Okay. So this is what the code does. It's you can clearly see the analogy with the tabular sarsa, and in fact, there is a remark which is valid in this case as well. So if you use linear approximation so you write down your Q as, so there are two remarks, Q as sum over I, Wi, Xi, Sa. So this is your linear expression for your Q. Then the gradient of Q in capital SAW, which is the eligibility that you have to put up there, is just the feature vector SA. So the gradient here means the derivative with respect to each component of Wi, each parameter Wi, and the X as the corresponding input. So I could also write this as grad I Xi, or this grad I is just D in DWI if I want to be super explicit. Okay, so this is the gradient. So you update the parameter Wi with the eligibility grad with respect to component I, and then your temporal difference error in this case has a relatively simple expression because it's just the reward plus gamma, the row matrix of weights times the feature in the new state actions minus WTX. Okay. So once you have this linear approximation, everything is very easy. In particular, the remark number 2 is that if the features, if X as I, okay, if I actually goes, is actually a pair of indices, so let's call it I1, I2, and this pair of indices actually corresponds to the product of the number of states and numbers of actions. Okay, so that in practice, if you choose as features I1, I2, features that identify the states and identify the actions. Okay, so this is just like looking at the orthonormal basis of unit vectors which point along the axis or of your state action space. In this case, semi-gradient sarsa falls back into tabular sarsa. Okay. So this is again is a sanity check, which means that if you do linear approximation and choose a sufficiently rich basis, then you're basically doing tabular sarsa. But the point here is, of course, that you would like to use less parameters than the number of states and actions that you have the problem. Okay, very good. What can we know? What can we say mathematically about this algorithm? It's not an exceptionally difficult proof, but it requires a lot of manipulations. Part of it is also part of this. The mathematical ingredients needed for this proof are contained in the book by Sutton and Bartow. So we just don't go very much into the details. Suffice it to say that there is a similar result as the one that we had for value approximation. Okay, so basically, one can prove that, sort of loosely speaking, the distance of my Q function for the parameters at which the algorithm converges. Okay, so my algorithm converges to some W parameter of Sarsa. Okay, so this is where the W go to when I repeat many experiments, minus the actual Q star. Okay, is something like is bounded by an object like 1 over 1 minus gamma times the distance in a certain sense, again, between, sorry, what I wanted to say, in fact, is more like something like this. So this is an equivalent of the value error. Okay. And this is on the right-hand side, we have the minimum overall W of the same value error. Okay. So this is formally the same results that we had for the value function when we had a fixed policy, but now we have replaced the optimal policy, etc. So if we can, basically, if our approximation is good enough to capture the optimal Q function, so if the subspace intercepts the optimal Q function, then also the approximation algorithm with Sarsa will converge to that, which is a strong result. If it doesn't, it fails by an amount which is given by basically the distance between your hyperplane of approximations and the true optimal value times a factor 1 over 1 minus gamma, which can be extremely large if your horizon is long. Okay. Nevertheless, this is a sort of mathematically useful result because it tells you that the algorithm is behaving more or less properly. It's doing what you expect. Good approximations, good results, bad approximations, bad results, and how bad they are depends on how many times you run your algorithm. Okay, that is the what is contained in the horizon of the problem. Okay, very good. Then the next question that we might ask is, what about off-policy algorithms? So off-policy algorithms are, for instance, Q-learning. Why is Q-learning an off-policy algorithm? Because when you construct the temporal difference error, you remember, so recall tabular Q-learning. So the behavioral policy is epsilon greedy. Okay, so you choose actions according to the epsilon greedy strategy. So for every time you have a Q, the estimate of your Q value, the policy is choose argmax of Q with probability 1 minus epsilon, or any other action with probability epsilon. Okay, so this is the policy you derive, and that's always the same that we're talking about. But what is the target policy? Here we have to look at how the temporal difference error is defined in Q-learning, and it is defined as follows. I recall you. In tabular Q-learning, it is gamma, and you take the maximum over actions at the next step, at the next state. So the target policy is not epsilon greedy, it's fully, entirely greedy. So you're using two different policies to estimate the temporal difference error and to take actions. This is why it's called off policy. Actually, the class of off policy algorithms is much wider than Q-learning, but we now focus on this particular instance because we've been discussing this before. Okay. So the question is, can we mix in Q-learning with function approximation? Okay, so now we're going to discuss in detail one very simple example of a Markov decision process, and we are going to see what happens when we mix Q-learning with function approximation. Okay, so we're just going to work out an example. It's something that you could code for. You could write the code which tries to solve the problem. But we just basically do the computation by hand, in a sense, okay? So the example that we have in mind is very simple. It's an MDP, which is comprises state 1. From state 1, I can take only one action. There's just one possible action, which brings me to state 2. Okay, so the probability of going from 1 to 2 is 1. I always go there. Then from state 2, I can take two actions. There is an action 1. Okay, there are two possible actions, action 1 and action 2 from state 2. And action 1 sends me to a terminal state with probability 1. So a terminal state is just a coffin. If the process goes there, everything stops. And then you have to restart again. And you restart the process again from 1. On the other hand, 2 sends you back to the state 2. Notice, everything is very simple so far. Probabilities are always, transition probabilities are either 0 or 1. There's no stochasticity whatsoever. Okay, so it's super simple. If you take an action, you go somewhere. No problem. Now, let me specify a little bit the parameters for this problem. So the rewards are all 0. So this is a problem where any action you take, you don't get ever any reward. They are not even 0 on average. They are deterministically 0. Okay. So this is very silly. Okay. But I'm explicitly constructing a super simple problem. Okay. My gamma is 1. Okay. There's no problem whatsoever here to set gamma equal 1. because I have a terminal state. The only thing I have to be a little bit careful about is that the policy that I have to choose to go between 1 and 2, okay, should be such that with probability 1, I end up in a terminal state. But this is not going to be a problem with Q-learning, because whatever I do, there's always some epsilon which takes me to the terminal state, okay? Now, I have now at this point to introduce function approximation. So put as it is, okay, just as an MDP, if you try to use any algorithm, dynamic programming, if you know the model, Q-learning, SARSA, if you use tabular versions of this, if you're model free, clearly the solution is that all the values are 0. So there's no reward whatsoever. The true values of any policies it doesn't matter what you choose. If you choose action 1 or action 2, you always get 0. Okay, so this is the sort of the dream for a reinforcement learning problem. There's nothing really to learn, so you know from the outset what the problem will look like. But now we are doing some function approximation. What does it mean in our case? It means that here we have 3 Q functions, okay? Remember, Q functions are functions of states and actions. So we have 3 of them, okay? So one of them is associated to this state action pair. Okay. So this could be our Q of state 1 and action whatever. Let me call it action 0. It doesn't do anything, okay? Then I have another object, which is state 2 action 1. This is my Q21. And then I have a third object, which is state 2, but action 2. And this is my Q22. Okay, so the space of my Q functions is a 3-dimensional space. There are just 3 possible Q functions here. Now, what I'm doing here, I want to do linear approximation. Okay, so this is something which we know it's relatively tame, shouldn't pose any big problem. So linear approximation. And the particular linear subspace that we are considering of this 3-dimensional space of Qs is constructed as follows. So I'm going to state that, my approximation for the red, so let's use the red, so everything is going to be more readable afterwards. So my approximation for state 1, action 0 as a function of W. So there's just one single parameter here by choice, because I choose that I want to approximate this with a line in my 3-dimensional space. So my approximation for the value is W is something like this defines, if you wish, this defines the value in the state 1. But then rather than choosing a different value for state 2 and action 1, I decide that this is W halves, okay? So I am parameterizing my value and saying, okay, in this 3-dimensional space, there is a line which depends on one single parameter W, and I am assuming that my Q function in state 2, action 1 is W halves. And then I'm doing something very similar for the Q function in 2, 2 as a function of W. And I say that it's twice W. Okay, so fair enough. I mean, this is a linear approximation, but clearly W equals 0. If I set W equals 0, this gives me all the Q's equal 0, which is the true solution of my problem, right? This is actually the value of any policy, and in particular, the value of the best policy, right? Okay. So given the setting, what can possibly go wrong? We have a linear approximation. This approximation can capture the exact solution of my learning problem. I use an algorithm now, which is Q-learning, and see how this algorithm behaves. Okay. So for Q-learning, I have to define my parameter epsilon. Okay. So let's assume also that W is larger than 0. And let's see what Q-learning does. Okay. So let's start our analysis from state 1. Okay. So, and we are going to use the same version of SARSA, but now with the error defined in the Q-learning sense. Okay. So let me write it here. So Q-learning with function approximation, this will tell me that I have to take an error delta at each step, which is going to be the reward plus gamma times the maximum overall possible actions of my weight vector in general, okay, times my feature at new state S prime, and I have to take the maximum overall possible actions S prime minus WT feature X S A. So this is the definition of the Q-learning error with function approximation, which again, if you choose properly the features, reduces to the usual tabular estimate. And then, and remember that the eligibilities in our case are just the vector eligibilities, the vector of features. Okay. And at every step, you choose your behavioral policy according to epsilon greedy. Okay, so that's how Q-learning combined with function approximation would look like. So let's do it, and let's consider the first step here, the red one. So we start in 1, take the only action that is possible. We end up in 2. Okay, and then we compute the temporal difference error to update our parameters. Okay, so the general rule would be that W prime would be going to be this times red Q. So we're going to apply this. So this is the red step. The red step tells me that I also have sort of I also have to specify where I'm going to end into state 2. Okay, 1, 2. So red is not a good idea here too, because it mixes up things. But let me do it in white. Okay, so this is the first step of our algorithm: state, action, new state, reward is 0. Okay, so what happens to my weight parameter, which is now a scalar? Okay, it's just a single scalar here, W is real positive. It is the previous value plus alpha. Okay. Now let's write down the temporal difference error, which is here up above. So the reward is 0. Oh, sorry, I said I made a little bit of confusion because I said that gamma is 1, so I can forget about this here. Yeah. So then I have plus gamma, which is 1, like I said. Then I have to take the maximum, okay, of the Q functions starting from the new state, okay? I go from 1 to 2, and then I have to compare the green and the yellow and take out the maximum of the two. But which is the maximum? Well, the green is W halves. Sorry, the yellow is W halves, and the green is twice W. So the green part is larger than the yellow part. So if I apply Q learning, then here I have to put 2 times W. Okay, because this is what is the maximum Q from the new state S prime equal 2. This is exactly maximum over all actions of Q in S prime equals 2, A prime W. And then I have to subtract the current value. So Q learning with function approximation gives me this update for the first step, which if you perform the trivial operations, just tells you that this is equal to W times 1 plus alpha. Okay, so far so good. We're just manually doing what your algorithm would do if you implement it. If you implement Q learning with function approximation, that's exactly what the first iterate would do. Then let's move to the second iterate. The second iterate starts from state 2. And then here, there are 2 possibilities depending on which action you take. Okay, here there is a bifurcation, right? So from state 2, if you pick action 2, which is the greedy one here, because it has the largest value. The green Q is larger than the yellow Q, so this is the greedy option. Okay. So from state 2, if you act according to the algorithm Q learning, you would pick the green action, which will bring you back to state 2. So in this case, what would be the update of the parameters? We have to apply Q learning again. So W second is the former W prime, which has just been updated in the first step, plus alpha, and then no reward. And here I have to put again, what is the maximum? So I have to put again this object. What is the maximum? Because the new state will again be 2. I go back to state 2. So what is the maximum from state 2? It's exactly the same thing here. So I have plus 2W. But then I have to subtract the current value, which is minus 2W. And then I have to multiply times 2. So this is the gradient of Q. Here there was a 1, which was the gradient of Q in S equals 1. And this is the gradient of Q in S equals 2 and A equals 2. Okay, so this is the eligibility. It doesn't really matter because, as you can see, these two terms cancel out. So under Q-learning, if you take the path through action 2, there is no update. W second is equal to W prime. And this is happening. This is happening. You take action 2. So action 2 is taken with probability 1 minus epsilon over 2, because this is the epsilon greedy recipe. Why epsilon over 2? Because with probability 1 minus epsilon, you take action 1. And with probability epsilon halves, you take action 2. And with probability epsilon halves, you take action 1 again. So if you sum up, that's the probability with which it happens. Okay? So again, first step from 1 to 2. Then second step, if we pick action 2, then we fall back to 2. But in this case, there is no update of my parameter. It stays where it is. Now, what happens if we take the other action? So we go from...
Hello, excuse me.
Any question?
Can I ask a question about, even though if this part here in, when you compute for the W double prime, the 2W here is W or W prime? Here, the one that cancelled out.
Thank you very much.
Okay.
Yeah, Carol is indeed correct. We are updating from W prime to W second.
Yeah,
Thank you very much for being more awake than I am. So what happens if we take the other action, the action 1, and this action will send us to a terminal state. So what is the update if we go from there? It's going to be W second equals to W prime plus alpha 0 plus now 0, because we are ending up in the terminal state and the value of the terminal state is 0. Okay, so this is a dead end road. But this is minus W halves, because this is W prime halves, because this is the current value for the green, for the yellow Q. Okay, we postulated that this is its value, times 1/2. So if we recombine everything together, then we get W prime 1 minus alpha over 4, and that's it. Okay, now that we've broken this into pieces, so let's see what happens in a full episode. Okay, so we are going to walk through this series of branches and see what happens. So from 1, we necessarily go to 2. Okay, and we make the first update of the weights. Then with probability 1 minus epsilon halves, we go into action 2, and then we repeat. But if we do this cycle here, there is no update of the parameters. So we can do this many, many times, but the parameters never change as long as we are here. And then eventually, with probability epsilon halves, we go here, and this will change my parameters. Okay, this is clear? So the only steps that change the parameters in one episode are the first one and the last one. Everything that happens in between or cycling through this best action, presumably best action, depending according to my estimate, everything that happens here doesn't change the parameters. So what can I write here is that if I summarize all this, so at the end of the episodes, my W final end is the W at the beginning of the episode. Let's call it W0. And then what happens? In the first step, the green one, I get to multiply times a factor 1 plus alpha. Then every time that I go through the action 2, I cycle back, but nothing happens. The parameters don't change. And eventually, at the last step before the episode ends, I get a 1 minus alpha over 4. Okay? Is it clear? I've been manually doing the iterates in this very simple case. But now this, I can write this as W0, 1. And then if I expand all the terms, what I find here is 3 minus alpha times alpha over 4. So after one episode, since this object here is larger than 1, after one episode, my new parameter is larger than the one I started from. But the true solution is 0, so it should decrease. So something weird is happening here. And in fact, if I repeat these over episodes and over episodes and over episodes, this leads to divergence. My parameters W go to infinity rather than going to 0. So this is true. I'm not doing any weird trick. I'm just following what the algorithm says me to do. Okay, then you could say, okay, fine. But then we know how to do things better. I mean, we have to sort of schedule learning rates. Okay, so maybe this is a problem of the learning rates. Well, not so much. I mean, even if I do alpha t that goes like 1 over t plus 1, say, something like this, or any other choice, it doesn't matter. Maybe it doesn't diverge, but still I'm taking the product of many numbers which are more than 1. So in the best case, I'm never going towards the true solution. Maybe I'm not diverging, but I'm going away from 0 anyway. This does not help. And neither epsilon does, the exploration. It doesn't really matter because you see, it does not appear after one episode. Because it doesn't really matter. It's enough for having a small probability of finishing, that's enough. Okay. So epsilon larger than 0 does not help. So what is happening here? So this is very, very interesting and very important because the root of this failure of Q-learning is actually much deeper than Q-learning itself. As a matter of fact, so there's been a lot of work on this on the literature, and there is a full chapter on Sutton and Bartow, which describes these issues with learning with off-policy algorithms, of which Q-learning is an example. It's a complicated chapter, so it's highly technical, and it's also difficult because this is still a field in motion. So we still don't have a clear picture about what to do with off-policy algorithms, even though they are important. So the key take-home message about off-policy algorithms like Q-learning is that, in the words of Sutton, there is one thing which is called the Deadly Triad. Okay, this is as close as we will get to a Quentin Tarantino movie title in our lectures. What is this Deadly Triad? It's a combination of three things, which are: one, function approximation; two, bootstrapping. Remember, bootstrapping is the part which you use when you have to construct your target in your semi-gradient method, right? And three, of policy. So behavioral is different from target policy. The combination of these three can lead to divergence of your algorithm, or anyhow to very bad behavior. But probably there are examples with divergence. If you remove any of these ones, things fall back in line. Okay, so this is really is a hardcore of difficulty. And there have been several attempts. You can read about this on Sutton and Barto's book, and still there is ongoing research on how to circumvent this problem. But the important thing here is to understand why any of these three things is important. So should we care? Should we really care about the existence of this Deadly Triad? Well, so what we can do is ask, can we remove any one of these three items and live happily without it? So can we remove item one, function approximation? Well, that's the easiest part of all. No, you can't. Okay? Because for every practical problem, the state space is just too large. Okay. So living within the tabular world is theoretically appealing, satisfactory when you write codes and they work, but it's not enough for most problems. So we cannot give up function approximation. So can we give up bootstrapping? Okay, this we can, okay, because we know that there are methods that allow us to do without. So do without one, no. Without two, maybe. But this requires Monte Carlo, for instance. Or other methods which use true gradient descent. Okay, so Monte Carlo is typically a poor choice because it has large variance, it's computationally expensive, so this is not necessarily the way to go unless your problem is particularly suited for that approach. Other methods, well, people are working on that. Okay, this clearly is an avenue for current research to develop other methods that are more sound and that avoid bootstrapping. Certainly an interesting point. But if we stick to temporal difference methods, can we do without three? So can we live happily just by saying, I don't care about off-policy algorithms? So far, the answer will be simple. I mean, I have a problem, I interact with my environment, well, I use SARSA, right? So what's the point? It's just it's equally computationally expensive. It does not bring any particular advantage to use Q-learning if you know that it's so dangerous if you combine it with function approximation. So what's the point of studying off-policy algorithms? Well, the point is subtle, and you can think of it in the sense that, yeah, maybe you can, but you are slave to the behavioral policy. What does it mean, you're a slave to the behavioral policy? In order to, suppose you have to train a robot, okay? So a very expensive robot, and to train it, every episode takes 1 hour, okay? Because this robot has to learn how to walk around, to climb a hill, etc. If you don't use offline learning, of policy learning, you have to do everything repeatedly. So you try and you improve, you try and improve, you try and improve. You have to interact continuously with the environment, and you have to use the same policy that you used for estimating the error just to choose actions. But in these situations, you could do something smarter, right? Because you could use some other policy, a policy which is not optimized. So for instance, you decide, let me try with a heuristic policy. It's something I think it works pretty well. And then you use this policy to generate data. Okay, so the typical off policy strategy is 1, use some exploratory or heuristic policy to derive data. So you get your stream of states, actions, rewards, new states, new actions, new rewards, etc. So this is by your exploratory, your behavioral policy. This is the behavioral. But then you use this data with another algorithm, maybe offline, which aims at finding the best policy, which is a different one. Obviously, it's never necessarily close to it. If these two policies are close enough, if your behavioral policy and your optimal policy are close enough, then things don't go so bad. But you don't know in advance. So you use some exploratory policy to collect data, and then you want to optimize using some TD algorithm. And this is the point where the system fails, because you do not have the guarantees that it works. And there are examples taken from the book. You can read on them. Examples, the famous Baird counterexample about how off-policy learning fails. Okay. So this is so there are situations in which you really would like to have an off-policy algorithm with function approximation that works. But this is not the direction in which you should go. So are there other algorithms? Yes, there is a lot of work. And a possible approach to this problem we will discuss in the next lectures starting next week, which takes a route which is rather different from the very start. Okay, very good. So I think I told you all the basic ideas and concepts about what happens when you try to address temporal difference learning, that is model-free learning with value function approximation. And with that, I think we can stop here. Are there any questions? Okay. So if not, I'm going to stop sharing and stop recording.